Welcome to this exploration of one of the most groundbreaking discoveries in science, the discovery of the electron. This discovery was made by the British physicist J. Thomson through his ingenious cathode ray experiments. Thomson's work revealed that atoms, which were once thought to be the smallest indivisible units of matter, actually contain even smaller particles. This revelation fundamentally changed our understanding of atomic structure and opened the door to modern physics and chemistry. In the late 1800s, scientists were puzzled by mysterious glowing rays that appeared inside vacuum tubes when electricity was passed through them. These glowing beams were called cathode rays, but nobody knew what they were made of or why they behaved the way they did. In 1897, J. Thomson decided to investigate these mysterious rays systematically. His goal was to determine the true nature of cathode rays and understand their properties. This curiosity led to one of the most important scientific discoveries of all time. Thomson used a special apparatus called a cathode ray tube for his experiments. This device consists of a sealed glass tube with most of the air pumped out to create a near vacuum. Inside the tube, there are two metal electrodes, the cathode, which is negatively charged, and the anode, which is positively charged. When a high voltage is applied between these electrodes, a beam of cathode rays shoots from the cathode toward the anode. This simple yet powerful setup allowed Thomson to study the mysterious cathode rays in detail and unlock their secrets. Thomson conducted a series of clever experiments to understand cathode rays. First, he applied a magnetic field around the tube and observed that the cathode rays bent in response to the magnetic force. Next, he introduced an electric field and found that the rays were deflected by this field as well. Crucially, Thomson noticed that the rays always bent toward the positive plate, indicating they carried a negative charge. Finally, by carefully measuring how much the rays deflected under different field strengths, he was able to calculate the charge-to-mass ratio of the particles making up these rays. Each experiment provided vital clues about the nature of cathode rays. One of Thomson's most revealing experiments involved placing two charged metal plates on opposite sides of the cathode ray beam. One plate was positively charged and the other was negatively charged, creating an electric field between them. When the cathode rays passed through this field, they curved toward the positive plate and away from the negative plate. This behavior clearly demonstrated that cathode rays are composed of negatively charged particles. Since opposite charges attract and like charges repel, the deflection pattern provided undeniable evidence of the negative nature of these particles. Through his systematic experiments, Thomson made several critical observations. First, cathode rays definitely carry a negative charge, as proven by their deflection toward positive plates. Second, the rays travel in straight lines from the cathode to the anode when no external forces are applied. Third, and very importantly, the properties of cathode rays remain the same regardless of what metal was used to make the cathode, suggesting these particles are a universal component of all matter. Finally, calculations showed that these particles must be much smaller and lighter than entire atoms. These observations together pointed to a revolutionary conclusion. Based on all his experimental evidence, Thomson reached a groundbreaking conclusion. Cathode rays are not simply waves or mysterious radiation. Instead, they are streams of tiny, negatively charged particles. Thomson initially called these particles corpuscles, but they were soon renamed electrons. This discovery was momentous because it proved that atoms are not indivisible. The electron became the first subatomic particle ever identified, fundamentally changing our understanding of matter and paving the way for the modern atomic model. The discovery of the electron had profound and far-reaching impacts on science and technology. It revolutionized our understanding of atomic structure by proving that atoms contain smaller constituent parts. In chemistry, the electron explained how atoms bond together and why chemical reactions occur the way they do. The discovery also laid the foundation for the entire field of electronics, leading to technologies like televisions, computers, and countless modern devices. In recognition of his monumental achievement, J. Thomson was awarded the Nobel Prize in Physics in 1906. His discovery remains one of the cornerstones of modern science.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.